Okay, so once again, good morning, everyone. We're about to start the webinar. In case you have any questions during the webinar, you can use the Q&A button on the below of your screen to ask us any question you can come up with. Either we will try to answer directly through the Q&A, or we will answer your question live at the end of the webinar, where we have foreseen a 15 minutes Q&A session. So if any question pops up during the presentations, feel free to already enter it in the Q&A, and then we can provide you with an answer at the very end of the webinar. If there are any technical issues you're encountering, you can contact us directly through the chat. And yeah, for your information, this webinar will be recorded and published on our project website after the webinar. So now I would like to pass the floor to Silke from Vista, who's the project lead of the ARIES project, and she will kick off this webinar officially. Go on, Silke.
Thank you so much. Yeah, welcome also from my side. My name is Silke Mikdal. I'm one of the two managing directors of Vista. We are a remote sensing and value adding company based in Munich in Germany, and we are the lead for the ARIES project, which is one of the EO Africa Explorers by ESA. I will give you a quick introduction. Come on, into our project and our goals here before we go into the depth of it all and show you the results that we have achieved. So, what is our goal? Within this project, we wanted to develop experimental Earth observation analysis techniques that use high resolution hyperspectral and thermal data for drought monitoring mainly. So to make plant and water and drought indicator products available. And we wanted to make them also available on an online platform. So we'll show you the results from this as well as the platform where you can find the results and the algorithms that we developed. This is an initiative by ESA also to inform future missions, because for now, both the hyperspectral and the thermal data are not quite as operationally available as many other data, like the multispectral data from Sentinel-2, for example, or Sentinel-3. Right now, these are mainly research data sets. But in the future, ESA has what's called the expansion missions, where the Copernicus program will be expanded also with a hyperspectral and a thermal satellite, which will then be able to produce these drought monitoring products on an operational basis. So this is a preparation for that as well. And of course, within the project, we also want to share our knowledge. And this is something why we're here today. From our side, we are three partners in the project. That's us, Vista, then Vito from Belgium and Liz from Luxembourg, and they'll introduce themselves. And then we also have different test sites and different African partners. So our test sites are in Senegal, Mali, Niger, and Zambia. And different products will be shown for the different test sites today. The different test sites do have different focuses, so I'm going to show you really quickly here the requirements. Overall, our main focus is the impact of drought and water stress, but both on crop and of forage productivity at a high spatial resolution and high temporal resolution. So you can imagine if you have cropland monitoring and mainly irrigated cropland, that is something where you need near real-time information, because if I need to irrigate my fields, more or less, I need to know that immediately. And I also want to know this at sub-field scale if I have, for example, a variable rate irrigation system, so that I can really do precise irrigation at every point in the field. So this is something where we need data fusion and augmentation techniques. For rangeland monitoring, on the other hand, the spatial and temporal needs are lower compared to the cropland monitoring. Overall, our main challenge is translating the crop water stress and productivity indicators then into information on drought onset, duration, and impact, as well as for irrigation advice. Those were the requirements with which we set out to have good results. And this is my quick overview here on what you will hear next. So this is the quick introduction into the project. Then you'll hear all about the thermal indicators and the results that we got from them, from LIST and V2. Then I will tell you a little bit about the hyperspectral indicators and what we saw in those. And finally, Nicolas from Vista as well will show you the platform, the Food Security Explorer, on which we've integrated the results. And then there's the Q&A. And that is already it from my side. And I will give over to Aolin now.
Yeah, it's my turn. So let me share my screen. Can you see it?
We see it, but not in presenters mode yet. Now it's in presentation mode. Perfect.
Okay. From the LIST side, we're from Luxembourg Institute of Science and Technology. So from the LIST side, we are mainly working on using high-resolution eco-stress land surface temperatures to monitor agricultural drought. So here's the title of our manuscript. We are now submitting it to RCE, and it's under review now. And so here, there are a lot of definitions of drought, and like atmospheric drought, agricultural drought, hydrological drought. So for the agriculture specifically, we consider soil moisture as a key indicator of the agricultural drought. But when we focus on Africa, there are very limited soil moisture ground size. So it drove us to use remote sensing to help us to monitor these signals. But unlikely, currently there are very limited high resolution soil moisture products because the signal is very weak. So if we want to monitor the agricultural drought, we definitely need some like a high resolution at the field level. And we have other indicators from other remote sensing bands to monitor drought. And people already developed many drought indexes. But in Africa, the sensitivity of those indexes should be double checked. And at the same time, recently we already have the EcoStretch high resolution LSTs. It is very special data because it is the first time that we can monitor LST at a different time in the day at high resolution. It's more like a geostationary, but with a higher spatial resolution. So we want to use the diurnal temperature range, those kind of new information at a high resolution to develop the new index. So regarding the achievement from our side, the first achievement, we did a very comprehensive sensitivity analysis of the developed drought indexes in sub-Saharan Africa. We include two soil moisture products from SMAP and SWI, which are soil moisture products using microwave data. And also we include some meteorological index and also the index calculated by the shortwave bands and also vegetation and temperature. We use 36 sites to did a comprehensive evaluation. Here's the map of the sites. And this is basically the summary of the evaluation results. First, we can see in the first two plots, the soil moisture products has overall very high correlation coefficient with ground measurements, but they have relatively coarse spatial resolution like 0.1 degree spatial resolution, which cannot be directly used for the agricultural drought mapping. For other drought indicators or drought indexes, they have relatively scattered scatter plot, which means their accuracy or their own sensitivity is not as high as the soil moisture products. So this result drives us to develop a new drought indicator to map the agricultural drought at high resolution. And the second achievement from our side is we developed a new eco-stress-based high-resolution drought index. And in the first step, we did a liquid stress land surface temperature reconstruction because compared to other thermal data, the eco-stress LST has two characteristics. First, it has a variable crossing time, which means the crossing time is not fixed. We need to, if we want to do some temporal analysis, we need a fixed crossing time. So, and even it has a relatively higher sampling frequency compared to Landsat, but still it missed some clear sky days. So we need to do some reconstruction to fill this missing days and also fix the crossing time. And the second step is we propose a easy equation to calculate a new drought indexes, mainly based on diurnal temperature range. And here is the theory behind this new index. So on the right figure, here is the diurnal temperature change in a day for different land cover types. We can see for the forest, it has the lowest diurnal temperature range. And compared to the barren land, it has the highest diurnal temperature range. So if we want to better use this information, we can classify different drought places and arid places, and then capture the aridity. And we also know that the RST changes is not only related to the soil moisture, but also related to the energy. So which means it mainly driven by two factors. One is energy received by the solar radiation or other energy sources, and another is soil moisture. So we want to minimize the impact from the energy, and emphasize the changes caused by soil moisture. So what we did is we borrowed the idea from the parent thermal inertia, which is on the left, defined at the left, which is the extraterrestrial radiation divided by the temperature range in a day. The on the top is the received energy in the morning, and this is the received energy in the morning, and here is the albedo, and at the bottom this is the diurnal temperature range. So which means the how many energy you need by increasing 1K for at a given pace. This is like if it is dry, it needs like very limited energy. But if it is very wet, it needs more energy to increase 1K. We did some changes. First, we changed the extraterrestrial terrestrial energy to the real downward solar radiation and also the atomic long wave radiation. And then we include a correction factor. This factor can help us to increase the sensitivity of the thermal inertia at validated regions. And for the validation methods, we use ground measurement from soil moisture to do some validation. First, we did some correlation analysis directly with soil moisture. You can see there are some clear signal cycles of the soil moisture. At the same time, we remove the signal cycles and only focus on the soil moisture anomalies from year to year. And then we did some analysis. So after we remove the signal cycle, we can see some clear drought period, which is a higher negative anomalies. Those periods we define as drought. And we calculate the correlation coefficients and to see, okay, if this indicator performs better than others. So here's the results for the LC reconstruction. So based on some temporal interpolation, we can see it has a relatively higher correlation with the ground measurements, and the accuracy is slightly lower than the clear sky retrievals, but still I think it's comparable with the clear sky retrievals at both noon time and midnight time. And here is the validation or the evaluation between the new indicator and the soil moisture. The blue points are the ATI, which is already developed, and the orange results are the results of our new indicators. First, for the blue points, which had developed the old version, we can see it has positive correlation with soil moisture. But when the soil moisture is higher, it has a clear saturation effect. because when the soil moisture is higher, the LC changes is mainly affected by the vegetation and also the energies rather than the soil moisture. So it decouples with the soil moisture. But after including correction factor, we can see that this effect, saturation effect, has been mitigated. So and the correlation has improved significantly at both crop sites and the other two grassland sites. So this kind of scatter plot proves this new indicator performs better than the previous one. And also we did some anomaly analysis, also the correlation over the all 36 sites. For overall, this is the overall pattern of the correlation changes at different sites with NDVI. Overall, as the individual increase, the correlation decrease because of the vegetation effect. But the new indicator, which is orange, has the overall better performance compared to the original one. And also we did some overall statistics of the correlation coefficient using this box plot across different sites, different land cover types. And this the last one, which is our new indicator, was overall better than the other indexes. And the first one is SWI, which is the soil moisture products. This is the best, but it has a relatively coarse spatial resolution. So we put it here as a reference, but we compare to other indicators. We can see it is the new indicator has the best performance. Here's the regional map. We mapped it in in Zambia, and we identified some crop regions which is surround, and we mapped this new drought index, and we can see it not only capture the irrigation event, but it also capture the difference across different crop fields. We can see this is the highest with the highest wet signals, but for other round places, it's not that high. Yeah. And this new indicator, we think, because it mainly uses the dynamic temperature range information, so we think this structure is well suitable for the future missions. So in the near future, until the end of this 2020s, we will have at least the three high-resolution thermal missions on schedule, which is freely available at 50-meter resolution, nearly daily frequency. So by integrating these three missions from NASA, ESA, and also France and India, we can do some high-resolution LST monitoring day by day, both knowing time and midnight time. So we as long as we have such information, we can have some near real-time daily monitoring of the agricultural drought by using this new indicator or new index. So here's the summary. We propose a new relative thermal inertia-based drought index. And this is also the first study that uses eco stress to directly monitor agricultural drought at a high resolution. And we also use a new eco stress LST reconstruction method. And we also did a comprehensive evaluation of the sensitivities of different drought indicators in Africa to soil moisture. Thanks. That's our results. I think the next one is Jerome.
Yeah, thank you, Aulin. I will take over now. Let me share my screen. There you go. So yeah, in the context of this EO Africa Explorers project, we at Vito, we also did some research on using thermal data to detect crop water stress at 20-meter resolution. This is mainly, so in the next 10 minutes, I will discuss our key findings of this research, which was mainly done also by my colleague Louis Snijders, and he's also preparing a publication on this, so more detailed information will also be available through that. But let's immediately dive in. So why do we care? First of all, as Silke already mentioned, if you want to increase the efficiency of your irrigation scheme, or activities, you ideally need to know as soon as possible when your crop is facing drought stress. Um, the problem with the current traditional vegetation health indices that we derive from Earth observation, for instance, the NDVI, is that it's not sensitive to this slight or first symptoms of crop water stress. For instance, if you see these two plants here on the slide, they will have the same NDVI value because they're still both green. Only when the plant are really partially destroyed, then you will see a difference in NDVI popping up, but then it's already too late. So the idea of the using thermal data is that um, early signs of crop water stress are much earlier visible through those type of data as compared to the optical data that is traditionally used. So what happens when a plant encounters drought stress? The transpiration of the plant is decreased, and as a result, the temperature of the leaves is increased. So this results in this higher land surface temperature. Um, and this is exactly what is measured by thermal data. So we propose in our research this simple concept of a crop water stress index, which is defined by the land surface temperature minus the air temperature. So we normalize for air temperature. And the idea is that relative increases in this indicator during the growing season are really pointing to drought stress happening on the field. So in this graph, the green curve represents the NDVI profile. So it's the grow you can derive the growing season from that, and then the red curve is our thermal indicator, and as soon as that peaks during the growing season, you know that your crop is in problems or has difficulties, and you need as a farmer to irrigate your field. In order to do this operationally, you obviously need high resolution and daily land surface temperature estimates, and that's a bit the problem currently. Like Aolin already pointed out, that we currently don't have a high resolution thermal mission to supply us with that kind of data. But luckily, researchers before us, they developed a method to cope with this lack of data. So what they did is they started from 1 kilometer Sentinel-3 thermal data, and they used Sentinel-2 data to artificially increase the spatial resolution to 20 meters. So this is just to give you a rough idea how the original data looks like and then how the upscaled data looks like. The problem is that going from 1 kilometer to 20-meter resolution, that's quite a stretch. So you can imagine that there's quite a bit of uncertainty in this involved in this analysis and in this final product. So what we did here in this project is we used the 70-meter eco-stress data to correct and decrease the uncertainty in the 20-meter sharpened product. So what we did is we took simultaneous observations from Sentinel-3 and EcoStress, and we checked whether there was any bias in the sharpened 20-meter data derived from Sentinel-3. Turned out that indeed the Sentinel-3 data was continuously and consistently overestimating land surface temperature as compared to ecostress. So based on this, we could already construct this cross-calibration equation, allowing us to correct for this consistent bias in the Sentinel-3 thermal data. That is one correction we applied. Secondly, we also looked into the issue of directionality, because depending on the angle in which you look at a certain field, the land surface temperature will be different. Here, this is illustrated in this figure. If you look at nadir view, so straight down on your agricultural field, you will see relatively lot of soil in there, and soil is much warmer than the crop. So that means that you will have a relatively high land surface temperature observed. If you, on the other hand, look from the side to your agricultural field, there will be much less soil in the image, so your temperature will be lower. That doesn't mean that the crop is suddenly more or less stressed. It's simply due to the composition of your image that the temperature will show these artificial variations. And of course, if you want to have a consistent daily time series of land surface temperature, you need to get rid of these artificial effects caused uh, by the angle at which you're looking at your field. So again, we used these observation pairs of Sentinel-3 and EcoStress. So for the similar location and time, we have different observations from different sensors under different angles. And based on that, we could construct this Vinnikov directionality correction. I'm not going into detail on these equations here, but just to show that they're actually relatively easy as long as you have acquisitions from different sensors under different angles, you can construct this correction equation and correct for these differences in viewing angles. We tested this and these both corrections that I just explained, and we showed that this drastically improves the quality of your land surface temperature estimates. So what you see in red are the differences between the Sentinel-3 and EcoStress temperatures originally before these corrections. So you see a consistent positive bias between them. If we apply the cross calibration, we get the green dot, so already closer to zero or no error. And then if we additionally apply this directionality correction, we get a much better match between the Sentinel-3 estimates of LST and the EcoStress LST. So we could effectively prove that our correction algorithms make sense and that they work to produce a better quality LST estimate. So we integrated these corrections into our calculation of crop water stress indicator. So on this GitHub repository, SenET OpenEO, we published our entire workflow of generating these crop water stress index at 20-meter resolution. So these are the steps that are involved. So we first download all the required input data from the different sensors that we need for the algorithm. We run this thermal sharpening SenET algorithm to generate the 20-meter LST data. We correct it using our using the correction steps I just explained based on EcoStress data. And then we compute this land surface temperature minus air temperature difference. So if you want to try it out, feel free to have a look at the repository there. Here are just some examples. We applied this methodology to our study site in Zambia, where we saw that in an irrigated field, there is clearly much less of these peaks in drought stress going on as compared to a non-irrigated field. So we were able to pick up these differences between irrigation and non-irrigation using this approach, which is quite optimistic, I would say. We also applied this in a study site in Mali, and there we noticed that things didn't work out as expected. One thing I should notice is that this is an agricultural site surrounded by basically a lot of desert, so only near the river there is agriculture going on. And here you need to keep in mind that we always start from this 1 kilometer Sentinel-3 data. And in order to do this sharpening to 20 meter correctly, you need sufficient amount of pure agricultural pixels, 1 kilometer pixels, which is here clearly not the case. So you really need to be careful when you want to apply this method that you apply it to a relatively homogeneous agricultural area. So what do we want to focus on on the future? So like Aulin already mentioned, there will be 3 new missions providing daily around 50-meter resolution thermal data. So in the future, we will be able to use that data instead of the 1 kilometer data as a starting point for our sharpening. What we should definitely always pay attention to, and this is a general remark for anyone who wants to work with thermal data, is you take proper care of cloud detection and removal, because we saw in our analysis that that is still a huge bottleneck. And also this correction of directional effect. So always take into account the viewing angle of your acquisitions before you actually use your land surface temperature data in downstream analysis. So these are 2 things we want to focus on in upcoming research at Vito as well. Thanks a lot, and over to Silke, who will present the results of the hyperspectral analysis.
Thank you so much. I think you have to stop yours. I can start my screen sharing. So then I will share with you the hyperspectral results now. So we're changing back from the thermal to the optical domain. Hyperspectral remote sensing means that we have sensors that can detect very many very narrow bands in different wavelengths. So we can detect much of the physical and chemical parameters that happen in vegetation. So this is in difference to, for example, the NDVI that Yaron mentioned earlier. Here with hyperspectral data, we can see a lot of different absorptions that can actually tell us what is happening with different chemical properties of the plant. So if you look at the right side at the spectra, only the very small part from about 400 to 600 nanometer is what we can see with our eyes. You can see where there's healthy green vegetation, that there's a little green peak at around 500 nanometers. And then blue and red, the chlorophyll absorbs. So there is the lowest part of the spectrum. And then there's a very steep red edge where we go from the absorption of the chlorophylls to the reflectance of the cell structure, where we can see really how much plant mass is growing. And then we see lots of small absorptions, and many of them are also water absorptions. So here we can really differentiate between what is biomass of the plant, what is water of the plant. And that is what we used here in this project to derive parameters for water stress. We used for this 2 sensors or 2 satellites. One is Prisma, that's an Italian hyperspectral sensor, and ENMAP, which is a German one. They are relatively similar from their from the information content they have, from the how many bands they have, and in which part of the spectrum they're looking. So we can use the same algorithms and methodologies for both of them. What we used is we used the so-called ENMAP box, which is a free and open source toolbox that has been created especially for hyperspectral data and can be used with ENMAP and Prisma. We used 2 main tools from this box. They're both in the agricultural part of the toolbox. One is radiative transfer modeling, and the time today is too short to go into the details of this, but we created a lookup table and then different lookup tables, and then inverted the ProSail model, which is one of the widely known radiative transfer models. This we did to derive leaf area and thus the biomass of the plants. And then we used the canopy water retrieval tool, which uses one of these absorptions of water that we can see in the spectrum to derive the plant water. These tools have also been integrated on the Food Security Explorer. Nico will show you more about that later. Our main test site was the test site in Zambia as well, which is AKTC's test site. This is the Agricultural Knowledge and Training Center in Zambia. They have several pivots, some of them photovoltaic operated, some of them from the main grid electricity operated. And they are doing a lot of research on their fields. So we use those. They also have some non-irrigated fields. So we have a wide variety of different conditions. What are the results now? We looked at 2 vegetation periods in 2023 and 2024. And we combined Nmap and Prisma to increase the revisit time because here, as we said, we have irrigated fields. You can see the pivots in the maps. So that means we want data as often as possible. Now for hyperspectral data, we're definitely not in the range of daily measurements yet. But you can see here that we have a relatively good time series. These are also not all of the images that we have, but they show you very well how the plants grow. You can see that there are different things planted in this big pivot here. You can see that the main the leaf area maximum is somewhere around the beginning to middle of July, before then the crops start decreasing. The green leaf area starts decreasing again, meaning the crops are maturing. If we look at the same results now in 2024, what we immediately see is that only half of the main pivot is planted. And that was due to the drought conditions. I think you probably all heard that and know that in Zambia there were drought conditions in 2024. So we can see that they didn't have enough water or enough electricity, actually, because a lot of the electricity from the main grid also comes from hydropower to plant the whole pivot there. When we look now at these individual points in the fields, we can see how the plants are growing over the season. And these are now all of the satellite images in one time series. And just in the different points, and we can see there are some areas where everything grows very well. This is here now 223. We're starting somewhere in May. Then the wheat starts growing and we have a very nice long growing period. The only point that doesn't behave the same way is this number 4 in this tiny corner in the north of the pivot, and seeding didn't work here. So this is why there's nothing really growing on there. If we look now at 224, what we can see is we had a long stretch of time where we didn't have any data here. And then even when we have data here, we're starting again in June. What we can see is that in June, the development of the wheat is definitely not as far. If you go here, this is about the same time in June, and the year before is definitely not as far as it was the year before. And of course, we have several points here, several locations where we have nothing planted, so there's also nothing growing there. So what we can see there is also due to the drought conditions in spring, the whole season kind of got shifted a little bit towards later in the year. Then we also had canopy water content, and we also derived that, and also for both years, because that's also very interesting. Now, what we can see definitely is that compared to the leaf area index, which uses the whole spectrum and is very robust, there is not much in terms of noise to see. the canopy water content only uses one of these small absorption lines. So any slight calibration things in the sensors can be seen. So you can see here sometimes there's a little noise in the images. But what you can also see is that we get very robust results in terms of we get a very good time series with a maximum in the canopy water content somewhere in July. If we're again looking at this in 2024 now, we can see that here the drought conditions are also visible. If you can see, this is the same scale in terms of coloring, and we never reach the same height of canopy water content that we had in 2023. So we can see these drought conditions have an influence on the whole year. Now, what do we learn from this analysis for the future? So ESA is planning a hyperspectral mission. It's called CHIME, Copernicus Hyperspectral Imaging Mission, which will provide operational hyperspectral data. It'll have much bigger scenes than right now. So our Prisma data is only 30 by 30 kilometer. CHIME will have 130 kilometer swath, so we can see a lot more. It'll have a 12-day revisit time, but will also be 30 meters. From the bands that it has, it will be comparable, hopefully with a better spectral calibration. And it will then be available globally. Well, now for Prisma and EnMAP, both of them, they only acquire over test sites, so you have to actually ask to get data from the different providers. Oops, what was that? So what is the potential for CHIME? It is, as we've seen, that we can see the different absorption features, for example, the water absorption, and can thus have a very clear view of how the plants are doing when there's water stress, how much water the canopy has, also how much water is in the individual leaves. And we can retrieve the variables with the inversion of the radiative transfer modeling. And the more information we have, the more individual absorption bands we have, the more plant parameters we can retrieve simultaneously, because the different absorption features are independent of each other. What are the limitations? The data volume of the hyperspectral data is far bigger than that of multispectral data. So already with our 30 by 30 kilometer scenes with the model inversion, it took very long. It took partially weeks if we wanted to do the whole scene. So that is something where we definitely need to work on the tools. And then also the temporal resolution of the data. For irrigation, we would like data more or less also daily. But CHIME will also have only 12.5 days revisit. So every 12 days around is the chance for an image. But if you look on the right, this is the chance for the images in the year, also taking into account cloud cover. And here we said that when there was more than 55% cloud cover over an area, then we can't use the image. And then you see, of course, in the Saharan desert, we have 24 images a year, so two per month. But as soon as we go to the areas where there's more agriculture, then we go down to 12 and then sometimes only 6 images per year, which means that is obviously not enough temporal resolution. So we need then to supplement with other data so that we have a stronger time series. And then, of course, we also have the spatial resolution of 30 meters, which means that we can see pivots and big fields. But for smallholder farmers with smaller fields, there's probably a size limit to the fields that we can actually analyze. And the recommendations we have are actually quite simple. We need a high spectral quality because, especially if you look at the right again, any calibration issues in a sensor will very much make themselves known if you use these small absorption features. And then, of course, we also want a high quality pre-processing, because here on the left, you can see two Prisma images and then an Nmap image. If you look at where the big pivot is, the geometric processing by the providers was not that great. So we had to do that ourselves and to look at every single image and see that it's in the right spot and correct this. And of course, this is something that would be much nicer if it was done beforehand, so that every single person doesn't have to deal with this when they want to analyze the data. And last but not least, we need the tools that can handle the data volume. And this is where cloud processing comes in. And this is where I give over to Nicolas, because he will tell you more about that. So that's it from my side. Thank you so much.
Thanks, Silke. Just share my screen. Can you see my screen?
Yes.
Yes.
All right.
Nico, I think you are muted.
Hello, hello. Yes, all right. My name is Nicolas Kotri. I also work with Vista, and I responsible the Food Security Explorer, and I do the first level support. So just for a brief introduction, what the Food Security Explorer is. Normally, what we used to do is like when we needed satellite imagery or computing resources, we had to go and look for it. So look for satellite images, look for server or computer where we can process this data. The Food Security Explorer tries to solve this problem and put everything together in one place for you as user to just to find it there. So if you need Landsat image or Sentinel or EcoStress data, you can find it there. And if you want to process it, you also can do it there. So it's a cloud-based platform. And the services that are offered there are science-based. So I will show you what we have integrated within this project. And well, that would be the short demo for today. So here you can see the landing page, our website. Here you can find useful information if you want to engage more with this project and this platform. I will show you the platform itself, where at the beginning we have data analytics and management tool. It looks like a normal browser, Earth Observation Explorer. Here you can search for data. For example, we have different catalogs. If we look for satellite, we have the Sentinel, Landsat, and other ones. I will show you just another pretty quick example about Sentinel. Let's here. Let's look for Sentinel data. Just pretty fast. It's through the search. So there you have. You can add this map, this scene to the map, and just start playing around or visualizing itself, trying to see if this kind of data would be useful for your studies. You also can change band combinations. Yeah, normal visualization procedures. Also, we have the EcoStress data sets. What was important for this project? The EcoStress data set that can also be searched within this data analytics and management tool. We have also a second user interface which is called SIR, Service Interface and Runner. And here you can process your data. So for example, the algorithms that LIST has developed are available here, and you can select them and choose the data for your specific area and just run it in here. I will show you some examples about how to find these services and how can you monitor the processing. For example, here I will go for the run option and the standard processing, and I will look for services. When you go inside, you see all the services available on the platform. I will show you the ones that we developed in this project, we integrated in this project. For example, where is it? The scale drought condition index, evaporative stress index, or the normalized difference water index, or the Kitch-Bryan drought index, KDVI. Let's say we want to process this one. We select it. It is a parallel processor. Of course, you have to select your data in advance, and just you click on output definitions and run the service, and this will automatically run. Of course, every run will cost you some coins, which is the currency that we use in this platform to monitor the processing needs. And once you click run, the platform automatically changes you to this monitor option, and here you can see how is your processing jobs, how are your processing jobs going. So for this example, it is a parallel processing service, so automatically this service starts six sub jobs, and here you can click one job and see in which step is this job going. So right now the job was scheduled, the data was fetched, and now we are on the step of processing. At the end, when the processing is done, you will get well, you'll see if it went right or wrong, and also you can see where are the output files. This is what the processor, the service results, the output, and also you can see the logs. So it is very important for debugging if you're a developer. And then, well, we have also another option, which is the developer. So if you want to go one step further and develop your own service, you also can do it on this platform. You just have to create one service and just develop it. This may be for this webinar a bit too much of information, but what I wanted to show you is that you can use the Food Security Explorer to run the services and the algorithms that had been integrated in this project. We also have a QGIS with an Nmap toolbox available that you can also run on this platform. I mean, not just algorithms, but also application, desktop applications as a QGIS. For example, here I have started the QGIS with the Nmap toolbox. So you can just go in and see a QGIS environment with the data that you have uploaded. For this case, I have used just a normal Sentinel-2 data. Let me just show you zoom to layer. Where is it? Zoom to layer here. And then you can see it. And as a normal QGIS, you can do your processing here. Let's say where you can create an NDVI using where are they? The band 8 and band 4 for Sentinel. Also, we have the Nmap toolbox if you want to use some or process some hyperspectral data. The toolbox is already installed there. Everything is there for you, ready to be used. So you just need to go in, to create an account and use the data, use the tools, use these applications. Yeah, that would be in a nutshell what the Food Security Explorer is and how these algorithms, science-based algorithms were integrated in the platform. And if you need more information about it, just please visit the website and contact us. We are happy to support you and with your projects. Yeah, that would be everything on my side. I'm open to questions if there are some. Thank you very much.
Thank you, Nicholas. Maybe I have one addition to the Food Security Explorer, just very quickly, that also the Food Security Explorer is part of ESA's network of resources. So you can actually go to the network of resources and ask ESA to sponsor some processing needs that you have there. So ESA will then give you a voucher, and you can also then use the platform for free by using this network of resources. So that is maybe an interesting option.
Thanks, Silke. Good enhancement, yes. So here you can see the network of resources. Just go to the network of resources-discover.org website, and then you can get your sponsorship for using our platform. Thank you very much.
Thanks, Nico, and thanks to all the speakers again. So actually, this marks the official end of our presentations and our webinar. We had foreseen a short Q&A session still. If there are any burning questions from the audience, please share them with us through the Q&A. So far, I don't see any burning questions yet. So maybe a question from me to Silke. We were actually recently in Zambia with the project, visiting some farms there. And there, Vista actually showed how these innovative indicators based on hyperspectral data can actually be used in an operational sense to support farmers in their decision making. So maybe, Silke, if you can comment a bit on this, how you see this in practice.
Yeah, this is a very good question. Thank you. We are already giving some irrigation advice to farmers in Zambia. And for that, we use the water content and the leaf area to derive water demand, so that we know how much water do the plants need. And then we also need some information from the farmer about their irrigation system, because of course irrigation is not just how much water will I irrigate, but also over how much time will I irrigate that. And then what we do right now is we give an irrigation advice always for a week or 2 weeks. How will the next few weeks look like? This also takes into account then how will the weather in the next few weeks be. So we also use the short-term weather prognosis for this. So it's one step further, it also has to integrate the multispectral data analysis, because as I said, the hyperspectral data is not available often enough yet. So we also use the Sentinel-2 data here, so that we have a really stable and robust way of also delivering data very regularly. Because of course, for the irrigation, you need to schedule this always in regular intervals. But this also really helps to preserve water. We know from several farmers, for example, they have reservoirs, and due to drought, the reservoirs are rather empty right now. And then you really need to see that the water that you have available is available over the whole growing season. Because if you spend it in the beginning of the season and then no rain comes and you have no water for the rest of the season, then your harvest will fail. So this is also something that has to be taken into account. How much water do I have? And this is also something where on a big scale, this information is quite often not available yet. So individual reservoirs, but how is it for whole countries, for whole regions? This is something that also needs more work. And maybe I give a question back to you now, because this whole thing with the water availability in whole countries. So Vito is also working on policy highlights. So maybe you can tell us a little bit of what the results of this project mean for policy, or where you see that this kind of information can help.
Yeah, thanks, Silke. So indeed, what we focused on right now in the webinar is mostly the scientific output of the project. So the development of new indicators based on these precursor missions, which are also, yeah, like you mentioned, not always operational yet. But what we're looking also at as part of the project is how these indicators can potentially assist agricultural policies in African countries, right? So often there is a push for climate smart agriculture, or a focus on preserving water resources, as you mentioned, in policies, but government legislation, they don't have really the means to monitor this effectively throughout the country. So that is why we are producing this policy highlights report, where we indeed show how the indicators that we develop, but also other innovative solutions being developed in the field of Earth observation, can really contribute to better monitoring agricultural policies at country scale, at regional scale, etc. So if you want to learn more about that, please take or keep a close look on our project website and LinkedIn page, where we will also disseminate these reports there. So yeah, I think if there's no other questions from the audience, unless any of the speakers would like to add a last word, I think we can officially close this webinar. So thanks a lot for attending. We were really pleased to be able to show you our achievements of the project. We really believe that we did very nice work and pushed a bit the boundaries on what is possible using upcoming hyperspectral and thermal missions. We also do believe that very exciting times are coming up with all these new missions being launched, and we should definitely, as a Earth observation community, be ready to make full use of that wealth of data that is coming in. So through these exploratory research projects, we hope to, yeah, optimize the potential of these new missions. So thanks again for joining, and yeah, hope to see you in another occasion or on a similar topic. Thanks a lot.
Bye.
Thank you. Bye.
Thank you. Bye bye.